Hi everyone, thanks for tuning in. This will be an ITCS 2022 talk on discrepancy theory. My name is Makrand and this is joint work with Nikhil Bansal, Haotian Jiang, Raghu Meka and Sahil Singla. So let me start by introducing the vector balancing problem, which will be the focus of this talk. So in this problem, you're given vectors v1 through vt, t vectors. They are d-dimensional vectors and they all have Euclidean norm at most 1. And our goal is to partition these vectors into two classes so they are roughly balanced. So one of the most popular problems about balancing vectors is the so-called Combinatorial conjecture, which asks whether we can assign these vectors plus or minus signs so that when you add these vectors with the corresponding assigned signs, the infinity norm of that vector, which I will also call the discrepancy vector, is constant. So if you assign these signs randomly, the infinity norm could be as large as square root t, but the Combinatorial conjecture asks whether you can make each coordinate of this sign sum vector to be constant. So this is a very famous problem in discrepancy theory, and it's a very strong conjecture, and it implies several other well-known conjectures. For instance, the Beck-Fiala conjecture, as well as other popular results like Spencer's theorem, which you might have heard of. So the best known upper bound we have towards this problem is due to Banashik, who in a very nice result showed that the discrepancy or the infinity norm of the sign sum vector is at most root log of the dimension d plus root log of the number of vectors t. So this is the best we know so far, and there is no known lower bound. As far as we know, this conjecture, Combinatorial conjecture, could be true. So this is the vector balancing problem about the final sign sum vector. Let me introduce a variant of this problem, which would be the prefix discrepancy problem. So here we not only care about the final sign sum vector, but also about all prefixes of it. So if you stop at any point t, little t, in 1 to t, and look at all the vectors until that point, and with the corresponding signs, what is the minimal infinity norm of any prefix vector? And surprisingly, the best upper bound for this problem is the same as for the Combinatorial problem. This is again due to Banashik, it's square root log t plus square root log t. So essentially looking at the final prefix, final sign sum vector or all prefixes so far doesn't make a difference in this bound. I mean, the proof is different, but the final bound remains the same. So this is again a very natural problem in discrepancy theory, but it also has connections to other problems. For instance, it implies bound for another very famous problem called the Stein's problem, and it has several applications in integer programming and approximation algorithms. So our focus on this talk will be understanding this prefix discrepancy problem. So what kind of constraints having prefixes in the problem put on our algorithm or our bound? So some motivating questions that we'll consider in this talk are the following. So first, is Banashik's bound optimal if we consider all prefixes, or can you prove a lower bound? Maybe it's much harder to prove a lower bound for the Combinatorial problem, which only considers the final sign sum vector, but maybe it's easier to prove a lower bound for the prefix discrepancy problem, or maybe there is a better upper bound here. And the second very natural question that one can consider is the following. So if you look at the prefixes of the vectors 1 through t, one can view this as a ordering based on the line graph, which is just the path between 1 to t. But we can consider other orderings between these vectors given by like a tree or a DAG, and the corresponding topological order on this DAG or the tree. And one can ask, what if we consider prefixes that are given by this tree or this DAG. What is the best bound one can hope for in this setting? Does Banachik's bound still hold here or not? And lastly, one needn't stop at prefixes of a tree or a DAG. One can ask, what if the discrepancy constraints are given by an arbitrary set system? And we introduced this problem, which we call the combinatorial discrepancy problem, and this generalizes all the other questions, and it also connected to some previously studied notions in discrepancy theory, and we will see that later in this talk. So these are the motivating questions for this talk. So what did we prove in this work? So first, towards understanding whether Banachik's bound is optimal for the prefix discrepancy problem, we show that this is not true in a smoothed setting where you're allowed to add a small noise to the vector. So if you perturb your vector by adding a small noise, and the noise here could be quite general, all we need is that the covariance matrix of the random noise vector you're adding has sufficiently small projection in each direction. So the projection is at least epsilon or something. So in this case, we can show that one can improve the Banachik's bound exponentially in the number of vectors t. So the bound is root log d plus root log t with high probability over the random noise. For instance, if the number of vectors is exponential in the dimension, then this gives you an exponential improvement. So the smoothest setting here, this also captures the random setting where each of these vectors are chosen IID from some distribution, and which has been studied recently in relation to several long-standing open problems in discrepancy theory. So this bound also applies to a random setting as well. And we also show that this bound for the smoothest setting, the root log v plus root log t, this is optimal even for a completely random instance here, assuming you cannot improve Banachik's bound in the worst case. So if Banachik's bound for prefix discrepancy is optimal, then our bound with root log t plus root log d cannot be improved. So this is our first result. So let me try to tell you briefly what goes into showing such a result. So let me call this quantity here in question to be delta. So we are given t vectors, and we want to give them plus minus signs, we want to color them. So what we will do first is we will partition these vectors into blocks or batches of m vectors each, where m will be polynomial in d and logarithmic in t. And now one can color the first block of m vectors here using Banachik result. And since there are just m vectors, this will give us root log t plus root log t bound just for any prefix of the first block. And for coloring the rest of the blocks, we adopt a iterative strategy. We will first find a fractional coloring of the block, which means that we will give a number between -1 and 1, which we'll interpret as a fractional color, satisfying some constraints, which will be linear constraints. So these linear constraints, what we would like to see are the following. First, once we reach the end of each block, then the fractional discrepancy with that color assigned to that block reaches 0. So after we have reached the end of a block with the corresponding fractional color assigned, the discrepancy becomes 0. So all the entire discrepancy has been cancelled out. And if we look at within each block and all the previous blocks that come before that block, then this discrepancy is at most delta. So these are two linear constraints and we find a fractional coloring satisfying these two constraints. And then once we have such a fractional coloring, then you can round this fractional coloring by interpreting this number between -1 and 1 as and using some bit by bit rounding. This is similar to an algorithm of Louvage, Spencer, and Westergombe that is used in rounding linear discrepancy and hereditary discrepancy. So this only incurs a factor of 2, this rounding. So the total discrepancy we achieve is at most 2 delta, hence our bound. And the key challenge or the key lemma we prove towards proving this, towards analyzing this algorithm, is to show that these linear constraints, which gives us an LP, these are satisfiable with high probability over the random noise we're adding. And this is a very technical part of the proof, and this relies on some very nice arguments using LP duality and some chaining arguments, because naive union bound is not enough to show that this LP is feasible with high probability. So I will not have any time to go into more details about this lemma. So if you're interested, please check out the paper. So this is the result about the first problem, about understanding whether Banach-Six bound is optimal or not. So what about if we consider prefixes of a tree or a DAG? For instance, if we are given a rooted tree and we are given 2-dimensional vectors at least, because 1-dimensional is trivial, then we show that Banach-Six bounds still hold in this setting. So we are able to show that the discrepancy for any such prefix is bounded by root log t plus root log d, same as Banach-Six. But in this case, this bound is tight. It cannot be improved if you consider prefixes of a tree. And this is tight even for a random instance. So I'm ignoring some log factors here when I'm saying this, but this bound is essentially tight, even for a random instance. So the prefixes of a tree or a DAG, they impose some natural constraints, which allows you, which makes you stuck at this bound. So what about a general DAG? So for general DAG, let's consider a very simple example first, just to understand what's going on. So suppose our vectors are just 1-dimensional, so they are scalars, and they're just 0, 1 vectors. And our DAG is the following DAG. It looks like this. So now we want the prefixes of this DAG to be balanced. For instance, the bottommost path, we should assign it plus and minus signs so that it's roughly balanced. But if we do that, then consider any of the top vertices and consider the majority color. For instance, let's say it's plus. So now if we have a path which sort of short circuits all the minuses in the top layer, then this path must have discrepancy that is linear in t. So in this case, we are very far off from root log d plus root log t bound, because the discrepancy for some prefix must be omega t. So this suggests that this bound of root log t plus root log t is not the right quantity to compare it to. So for a general DAG, there are many more constraints. The number of paths can be a lot more. So what is the right bound here? So as we'll see in a second, the right bound will be coming from what's called the hereditary discrepancy. So let me introduce this notion, which is a very well studied notion in discrepancy theory. So let me start by defining the discrepancy of a set system first. So suppose we are given a set system on the universe 1 through t. And our goal is to give signs to the elements of this universe so that each set have so each set has roughly equal number of pluses and minuses. So we want to minimize the imbalance among all sets. So minimize over all choices of signs the maximum imbalance of each set. So this quantity I will call the discrepancy of the set system or the set family. So now the hereditary discrepancy of a set system is the maximum over all projections of the universe. So if you project our universe onto some elements and consider the induced set system on that on the projection, what is the discrepancy of the set system? And the hereditary discrepancy is the maximum over all such projections. So why is this the right notion to look at? For instance, if you look at this DAG that we just saw before, and our set system is all the prefixes of this path, of this DAG. So all paths and all prefixes of such paths. Then it's not very difficult to show that the hereditary discrepancy of this set system is linear in T, which matches what we were seeing before. And if we consider a different DAG, for instance, this very simple DAG, which is just a path, then the hereditary discrepancy of this particular set system, which is the prefix of this DAG, is just constant. So this gives us a very nice way to generalize Banachik's result from not just prefixes of a tree, but to an arbitrary DAG in the following way. We show that for if we are given any DAG and we want to minimize the discrepancy with respect to all prefixes of this DAG, which can have a lot more path than a tree, then the right quantity to compare it to is the hereditary discrepancy, and the bound we give the discrepancy in this setting for any arbitrary d-dimensional vectors is bounded by the hereditary discrepancy of the underlying set system, prefix of the DAG, times root log d plus root log t. So for instance, if G was a rooted tree or a path, then hereditary discrepancy is constant. So this generalizes the previous results. So how do we prove this? So there's some very nice ideas that go into proving this, but the key lemma here is to sort of, we reduce the case of an arbitrary DAG to that of a tree. And this involves this nice combinatorial characterization of paths in a DAG. So we show that in any DAG G, there is always a rooted spanning tree, such that any path in this DAG has only few non-tree edges. Number of non-tree edges is just hereditary discrepancy of the set system of prefix of G, all prefixes. So basically, and how do we show this? So one can show this inductively by working backwards from the topological order and showing that whenever the number of non-tree edges increase by some amount, then we can find such a chain structure, which is this following graph, with one additional link, so with one additional triangle. And if you find such a chain structure, then it also implies that the hereditary discrepancy also increases. So you can charge the number of non-tree edges to the hereditary discrepancy. So once we have this lemma, we can sort of split the case of arbitrary DAG to hereditary discrepancy many disjoint trees, and for a rooted tree we can show that Banachik's bound still holds in this setting. And we do this by generalizing the convex geometric arguments that were used by Banachik. So we generalize them to show that this root log t plus root log t bound holds not just for prefixes of a path, but even for a rooted tree. And this gives us a result for the DAG. And to show that this bound is tied for trees, we can construct a very nice lower bound example, which is pretty simple. And let me just give you some key points here. So for instance, let's say we are given a tree and we want to assign vectors to this tree. Let's say this is just a complete tree, complete k-array tree. We will just assign two-dimensional vectors to each vertex of this tree. And I will ensure that along every path down this tree, the vectors will always be orthogonal. So the squared Euclidean norm will always increase along every path. So basically, if we have a binary tree, this will give us this root log t plus root log t bound. And even if you pick these vectors randomly, they will be sufficiently orthogonal. At least you can find such a subtree in a larger random instance. So this bound is tight even for a random instance. So this proves us the result about DAG and trees. And what if we consider an arbitrary set system where there is no such nice structure? So here we are again able to relate the discrepancy in this context when your constraints are coming from an arbitrary set system to the hereditary discrepancy, but with the polylog factors in not only D and T, but also the size of the set family or the set system. And to show this, we actually sort of show that the discrepancy in this combinatorial discrepancy problem with respect to arbitrary set system can be bounded in terms of the gamma 2 norm of the set system times times some polylog factors in D and the cardinality of S, the set family. Okay, so I'm not going to define the gamma 2 norm of a matrix. It's some particular norm that you can define for a matrix, which would be the incidence matrix of the set system here. And it is well known here that gamma 2 norm and hereditary discrepancy are related by at most logarithmic factors. So so that's how we get our result. So to summarize, first we looked at whether Banachik's bound is optimal for the prefix discrepancy problem. And we show that this is not true in a smoothed setting. The bound can be improved exponentially in the number of vectors t. And this is tight, assuming Banachik's bound is tight in the worst case. And but if we consider prefixes of a tree or a DAG, then we can prove a bound in terms of hereditary discrepancy, which generalizes Banachik's bound. And this bound here, this bound is tight, so you cannot improve this even in a random setting, even for a tree. Lastly, we looked at the combinatorial discrepancy problem, where again we're able to show that discrepancy constraints coming from an arbitrary set system, one can still bound this quantity in terms of the hereditary discrepancy with the worse polylog factors, where there's a parameter of cardinality of the set system as well. So that's a summary of our results. Let me conclude with some open problems. So one very natural question that is still left open by our work is whether the prefix version of the Combe-Rush problem is true or not. Whether if you look at all prefixes of the final discrepancy vector, can we find signs so that the infinity norm is constant? So we show that this is still possible as far as we know. And one can also ask, I mean, smoothed analysis is a nice idea in its own. So one can ask, for some of these long-standing problems like Combe-Rush or Beck-Fiala conjectures, can we prove them in a smoothed model? So recently, there has been a lot of work in understanding these problems in a random setting, where all these vectors are completely random, where we know that some of these conjectures are true in some regime of parameters. But what about if we are giving a worst case instance and we are adding a random noise? This will sort of at least clarify as some kind of structure on the lower bound instances of these problems. And third, for this combinatorial discrepancy problem, where your constraints are given by any arbitrary set system, our bound had a polylog factors which also is dependent on the size of the set family, which could be very large. So one can ask, whether this bound can be improved to just the hereditary discrepancy times root log t plus root log t, which is Banachik's bound, times the hereditary discrepancy factor. As far as we know, this could be true, and this will generalize a results from a DAG to any arbitrary set system. Lastly, there are always a question of, can we prove algorithmic guarantees for any of these results? So most of the results in this talk can be made algorithmic up to an additional log factor. So But can we achieve the root log t plus root log t bounds for with an polynomial time algorithm? That remains a very interesting open problem. So that's it. I will conclude with that. Thank you very much, and thanks for listening.